Hello, welcome back to lecture 2. In today's lecture, we are going to talk about the second law of thermodynamics and entropy. So just a quick recap of lecture 1. So lecture 1, we really talked about the first law of thermodynamics, which is just delta U equal to Q plus W. Q is the heat, W is the work, dW is minus PdV. P is the external pressure. And then this is the differential form of first law of thermodynamics. Essentially, first law of thermodynamics means the energy is conserved, right? In first lecture, we also introduce you the thermodynamic properties or state functions. PTVU, these are all thermodynamic properties, but Q and W are not because they depend on path, right? And then we also introduce enthalpy at the end of lecture 1. Enthalpy is H equal to U plus PV. And then we said enthalpy is also going to be a thermodynamic property. Okay. And then the reason why we introduced delta, enthalpy is delta H is going to be equal to H2 minus H1. And then for a steady state flow process, this is actually very useful. Basically, the change in enthalpy between section 1 and 2 is going to be equal to just like the Q plus WS, right? So this is the enthalpy, the use of enthalpy. All right. In today's lecture, we are going to establish on these knowledge and then introduce you the second law of thermodynamics and also introduce you another thermodynamic property, which is entropy. Entropy is usually S. We use S to represent entropy. Okay. All right. Today's lecture, by the end of today's lecture, you should be able to understand the directionality of processes and the concept of entropy, right? So first, we will talk about the different types of processes, including reversible and irreversible processes. And we can also talk about special processes, including constant volume, constant pressure, isothermal, adiabatic process. And then we will really focus on the second law of thermodynamics, and then introduce you entropy, and then the entropy, how one can calculate entropy change for reversible and irreversible processes. Okay, so first of all, what is a process, right? So in lecture 1, we talked about the system at state 1, let's say equilibrium state 1, and then equilibrium state 2, right? If you want to go from state 1 to state 2, you actually need to go through a change of the state. And this change of the state is actually called the process, okay? Now, the process can be reversible or irreversible. What do we mean by reversible? So reversible process is a process is reversible only if a second process can be performed such that the system and surroundings can be restored to their respective initial values by an infinitely small change in the universe. By universe, we mean system plus surrounding. So basically, we are not changing anything inside of the universe. We can actually go back to the initial state. Okay, so this is called reversible process. Now, by definition, irreversible processes is that when changes in the system which cannot be reversed in their entirety without making changes elsewhere in the universe, meaning that you have to do some work to actually go back to the original state. So this is usually called irreversible processes, right? Don't worry, we will give you some examples to better understand the difference between reversible processes and irreversible processes in the next slide. But just like I want to quickly highlight, the reversible processes, usually they have the following two characteristics. One is that the system is at equilibrium state at all times. So remember, if like the system pressure and the external pressure is equal, they are at the equilibrium state, meaning that during this change process, you actually control the external pressure or system pressure, maintain them like equal at all times. So you actually need to change very slowly. Okay, so usually it's a very slow process if you want to make sure the system, the process is reversible. Okay, now reversible process is also ideal. It yields the maximum work output during expansion or requires minimum work input for a specific process during compression. And again, for the next slide, we will tell you what these means. Okay, but just remember, reversible process, the system is at equilibrium state with the surrounding at all times, very slow process. And then reversible process is ideal, right? Ideal means that in real world operations, usually the process cannot like reach completely reversible. So that means your work output or work input, right, might be slightly different from these ideal process. We will talk about efficiency later as well, and use efficiency to quantify whether your process, how reversible your process is. Okay. All right. So now, what's irreversible versus reversible processes, right? What are their difference? Okay. So first, let's imagine this process. Our state one here is again focusing on a piston, a chamber containing a piston, and a chamber, a collection of gas, okay? So originally, let's say your piston, you have a mass weight, you have a weight on the piston. Weight is the mass is m, okay? A finite mass. Okay, then because of this finite mass, the mass is also exerting some pressure on the piston. The pressure can be calculated by force. Force is equal to m times gravitational constant divided by the constant cross-section area. So this is the pressure induced by the mass, right? And then you also have external pressure, P0 as your atmosphere pressure. So external pressure consists of P0 and the pressure exerted by the mass. So P external is going to be P0 plus mg divided by A, right? Now for state one, since it's at equilibrium initially, so P system, which is P gas, is equal to P1. P1 refer to state one, okay? So system pressure equal to external pressure. That's why you have state one, equilibrium state one, okay? And then let's specify the temperature T1 for state one is equal to T0, which is equal to surrounding T as well. So temperature is at equilibrium with the surrounding for the system. Now, what we want to do is that we want to change to state two, and then state two, basically the process we are going to take to go from state one to state two is by simply just like sliding this mass off the piston, and then you put it on the leveler here, okay? So you slide away, and then basically the external pressure now all of a sudden drop to P0, right? And then the mass is just sitting at this height, okay? And then when you decrease the external pressure, right, now your system pressure is greater than external pressure, so your gas will start to expand, right? And then basically, while your gas is expanding, then the system pressure is dropping until it drops to P0, where you reach another equilibrium state. So P gas, P2 is equal to P0, then you have it at equilibrium. Let's say the temperature is not changing at all, so still T0 in equilibrium with the surrounding temperature, okay? So this is your state two. Now, this process is basically like we just described, right? You are sliding the mass to the right platform instantaneously and wait for a long time. And then you have like your gas expansion. This is the process, okay? And then more specifics about this gas, let's say we pick an ideal gas. Now, ideal gas is really a theoretical gas composed of small gas particles. And then for ideal gas, your particle volume relative to the container volume is negligible. Okay, that means your particle distance is actually very large compared to their own size. So really, you are talking about like negligible intermolecular interaction. Okay, so that's the ideal gas. And for ideal gas, usually it follows ideal gas law, PV equal to RT or nRT, depending on the molar volume or total volume. Okay, and we will write down that equation for you later. Okay, so and also for ideal gas, the internal energy only depends on temperature. Okay. All right, so now for this process, let's just like focus on changing from state 1 to state 2. Through this process, we want to ask how much work you perform, okay? So the mechanical work, dW, is equal to, again, minus P external dV, and then P external is always P0, right? Because we are talking about the process, right? Within this process, the external pressure is always P0. So you can just like plug into this equation, and then you just need to take an integral, right? W is equal to changing from initial, which is V1, to V2 minus P0 dV. And then P0 is constant, so you can move out. And then basically it's going to be delta V. And that is equal to minus P0 V2 minus V1. Okay, so this is how much work you perform. And this work is like system performing work on the surrounding. Okay. And then you know it's going to be a negative value by convention, right? So minus P0 V2 minus V1 V2 is greater than V1. Okay. All right. So basically, if you imagine like trying to put this process onto a PV plot, right? PV plot is again like I said, for your system, if your system is ideal gas, right, inside the chamber, then the ideal gas P or P gas is equal to PV equal to RT, or P gas is going to be RT0 divided by V gas, since the system temperature is kept at constant at T0. So P is equal to RT0 divided by V gas, right? Now, if you're looking at like a PV diagram, so this is like, if you plot out the P gas versus V gas, then it should follow this line, because you have like P is equal to some constant value divided by V gas. So your system pressure will follow this line when it's changing during this process. So as your volume expand, your system pressure drop following this line. Okay, so this is the system pressure changing path. Okay. Now, when we are talking about external pressure, right? Initially, your external pressure P1 is equal to P0 plus mg divided by A. Okay. But when we are doing this process, we are instantaneously removing this mass. So the external pressure all of a sudden drop to P0. So your external pressure actually follow this path, right? Drop to P0 instantaneously and maintain at P0 instantaneously, right? Now, when we are talking, we already calculate the work down by down during this process, right? So W is basically minus P0, V2 minus V1, and then basically P0 is here, and then V2 minus V1 is here. Basically, this is the absolute, this is this area of this rectangle is basically just like the absolute value of this work, okay? So you can imagine this is like the work that done by the system, okay? Now we want to ask, right? So remember when we are talking about whether the process is reversible or irreversible, we want to go back to the original state. So let's say you want to go from state 2 back to state 1. How can you do that? I mean, to reverse this process, what you need to do is basically you just like, lift this mass up to Z2 and then just like slide onto the piston. Then your external pressure is going to be greater than system pressure, and then the piston will drop, and then this system will be compressed until the system pressure reach the original pressure, which is P1. So basically, all of a sudden you increase here, and then external pressure will follow this map, and then your system pressure during compression, it will slowly increase, okay? So now this is basically the overall, right? To reverse this process, you simply raise this mass to Z2 and then place on the piston. Now, for when you do this, right, you are actually lifting it up. So to overcome the potential energy, right? So potential energy is going to be mg force times Z2 minus Z1, right? So basically the height difference. So you actually need to overcome this much potential energy of this mass in order to reverse this process, right? So this WF reverse one is the actual work that needs to be done in the universe to reverse what path one did, or this path, the process one did, okay? So obviously, M is a finite value, G is a finite value, Z2 and Z1 is a finite value. So W reverse is a non-zero, a finite value. So you actually need to do actual work to reverse this process. So by definition, you are causing changes in the universe. So by definition, this is an irreversible process, okay? Now, imagine this way, right? Instead of removing one mass, like the mass, but you are decreasing the weight of the mass slowly. Like this will be a reversible process. Like, so this is the following, okay? So initially, let's say you still have V1, okay? The volume is the same, temperature is the same, P initial is the same. And then like basically what we are doing is that we are splitting this M mass into many, many small weights, but the total weight of the of all these mass is going to be still the same as M, okay? So if you split into 5, then you have like, M divided by 5 for each mass, okay? Or for each weight. Now what you are doing is that initially you just like slide 1, okay? On this level, you wait the system to expand to reach, you just slightly decrease the external pressure. And then you let the system pressure to reach external pressure and then equilibrium, right? Once let's hypothetically, let's say we'll reach this level, and then you remove the second, you slide the second mass to the this level. And by sliding, we are not doing mechanical work at all, okay? And then you decrease external pressure a little bit more, let the level increase a little bit more. Let's hypothetically you reach here, and then you slide another mass. You repeat this until, right, you move the last mass. And then it will just like, again, external pressure is now P0, and then T0, and then you will expand to the same state, right? The state 2 here and state 1 here are identical to the states in previous slide. But now this process, right, by splitting all like the mass M into many, many small pieces, you are actually slowing down like, the overall process. But later you will see, right, if you do this, then you can actually make this irreversible process into a reversible one, okay? And then this, n is the number of platforms, all equivalent to the number of like tiny weights that you have, right? And then delta M, if your N is going to be infinite, right? Increase to infinite. Basically, you are splitting this weights into like, infinite number of small, very, very tiny weights. Then your delta M or your M is going to be essentially goes to dm, right? Delta M is like every step you are decreasing the mass. Okay, it's going to be m divided by n. Okay, and then same thing. If you plot this whole process onto a PV diagram, again, initial state is the same, right? P1. And then the final state is the same, P2. And then as again, the system pressure, while it's dropping, since it's still ideal gas law, right? The system pressure will still follow this. But now what's different is the external pressure. External pressure, right? The first step, you are taking just one off, right? So you will just drop to like, P0 plus, N minus 1 times delta M, right? And then you will have a final value, let it reach equilibrium. Equilibrium means like the system will expand, right? So V2 expanding to this value. While it's expanding, then the system pressure is dropping from here to here. And then when it reaches equilibrium state, your system pressure is equal to external pressure. So it will rise here, okay? And then you take another one, same thing. Take another one, same thing. Take another one, same thing, right? Take another one until, so basically you move from point 1 to point 2 by many different small steps. Like in the previous slide, what we are doing is that you drop all the way here and then you wait until equilibrium. So we are going from this to now many, many different small steps, okay, until you reach 2. This is like we are talking about the external pressure and then like the expansion motion of your system, okay? Now, if our n goes to infinite, right, then you can really say this change is negligible. I mean, it's really tiny and then go back. Really tiny, go back. Really tiny, go back. Really tiny, go back, right? So actually, if your system, if you want your process to be completely reversible, basically what you need to do is that you have to make this like, really tiny, maybe like sand, right? You take 1 sand away. And then basically you are going to be the difference between your system pressure and the surrounding pressure will be pretty much like the same. So basically the system pressure will always be equal to your external pressure, right? So that's why we say the system is at equilibrium at all times. So if you do that infinitely, n goes to infinite, then your system pressure will follow this line, and then your external pressure will also follow this line because these steps are going to be really, really time negligible, okay? And then here we want to see, right? We can also calculate what is the, so as n goes to infinite, steps follow the isotherm. Basically, your external pressure equal to system pressure follow this line, okay? Now we want to ask the same thing. How much work we need to do in order to reverse this process. So in this process, what we need to do is that we just take this tiny mass, right? Bring it up to Z2 and then put it on, and then you just let a equilibrium go down, and then you slide back, slide back, slide back, slide back, slide back, slide back, slide back. Remember, sliding back doesn't make any work, right? So the only step that is making work is lifting this tiny mass from Z1 to Z2, and then this tiny mass is just like equal to delta M. Delta M is M, original M divided by N, right? So now as N goes to infinite, your delta M goes to infinitely small numbers, and then your delta W reverse is going to be vanishingly small, okay? Or you can say this work is negligible, right? So you can actually, by doing negligible work to reverse this process. By definition, this is an irreversible process because we are not causing any changes in the universe by reverting back to the original state, okay? So hope by now you can understand the difference between a reversible and irreversible process, okay? So now let's take a closer look at the this reversible process, right? We want to ask how much work that the system is performing on the external surrounding, okay? So now, since we said, right, during this reversible process, right, your external pressure is equal to the system pressure. And then during this expansion process, again, your system pressure is decreasing from P1 to P2 following this ideal gas law that we just established, okay? And then your external pressure also follows this line because you are creating many, many small steps, okay? So what you can do is that dW is going to be equal to minus P system dV, right? For reversible process, we said, right? Only this equation only works for reversible process because P external is equal to P system at all times, okay? So you plug in this equation, right? So dW, you integral this equation. W is going to be changing from V1 to V2 minus P system pressure dV, okay? And then system pressure is again equal to RT0 divided by V. So you plug in P system, RT0 divided by V. And then R is gas constant, T0 is constant. You can actually move it out, and then basically it's going to be minus 1 over V dV integral. And then we know that integral is natural log V2 divided by V1, okay? And then you move the minus sign in the front. So again, double check, right? Work expansion should be negative, right? These are all positive. V2 is greater than V1, so this natural log is going to be greater than 0, so positive. So you actually have a negative, right? So check, right? Sign check, right? So, but the W is going to be minus RT0 natural log V2 divided by V1, okay? And then on the plot, right? Basically, if you want to, you can mathematically calculate this work, but you can also, when you are doing integration, basically you are just calculating the area under this curve, right? So basically, you can highlight the area, and then the total area of this region under the curve is basically the absolute value of the work that you perform. So you do the math, you take absolute value, that value is going to be equal to the area under the curve, okay? So now, if we look at this reversible process, right? This is the total net work output, right? So this area, but the first step is just like the area under within this rectangle. So the reversible process actually perform more work, right? So just like briefly summarize the reversible process, like I mentioned, the system is at equilibrium state at all times, no temperature pressure gradient. And in order to achieve that, usually you are talking about a very slow process, okay? And then here, we already hinted, right? The reversible process is an idea since it's produced the best possible result. For example, it yields the maximum work output during expansion attainable, right? Like I mentioned, right? If you follow a reversible process, meaning that the external pressure follow the system pressure curve, and then the work that you down on the surrounding is actually just like the area under the curve, right? So the yellow highlight all the way, okay? But now if you go through that irreversible process, which means your external pressure all of a sudden drop to zero, and then let the system expand slowly until the external system pressure equal to the external pressure, which is at equilibrium, then the work output on the system, on the surrounding, is going to be just like the red rectangular area, okay? So obviously this yellow area is going to be much, much greater than this red area. So when we are going from an irreversible process to a reversible process, your work output is increasing during expansion, right? And then reversible process actually give you the maximum work output when you go from state 1 to state 2 during expansion, okay? And same thing, it will reversely, it will actually require the minimal work input during compression for a specific process, right? So when we are talking about going back to from 2 to 1, right? You can do the same thing. You can slowly increase the external pressure, right? In a reversible process, you can follow this way. And then basically this is the work that the system need to go back from state 2 to state 1. Or you can put the mass directly on top of the total mass directly on top of the piston, right? By increasing external pressure all of a sudden. So you increase the pressure all of a sudden to P1, and then you let the system compress until your system pressure reach the external pressure. So in that case, right, in this reversible process, you actually need, right, P, again, P is constant at P external is constant at P1, you're changing from V2 to V1. So the blue rectangle actually corresponding to the work input that is needed during this compression process. But this yellow highlight still is the reversible process, and you can see the reversible process during compression require the minimum work input, okay? So that's why we said, right, reversible process is ideal since it produced the best possible result. And then now, since like the reversible process is usually very, very slow in real world, right? We don't usually like operate the system like at a completely reversible process. So basically the result of a real process is going to be equal to real result of reversible process times some efficiency coefficient. Obviously, the efficiency coefficient is going to be a value between 0 and 1 or less than 100%. So let's say if you have a reversible process, you have the ideal result, but just times to a certain percentage, let's say 60 or 70%, depending on how reversible your process is, okay? All right, so that's coming back to here, right? Reversible process give you the best possible result, and then in real world, we don't usually achieve the best possible result. And then in the next few slides, we are going to really focus on Carnot engine, right? Carnot engine really involves completely reversible process. So basically, it's an ideal, you know, engine that involves complete reversible process. That means it gives you the highest possible efficiency for this Carnot engine. Okay, we will talk about Carnot cycle in a minute. Okay, all right. So I hope by now you understand what is a reversible process, its characteristics, and also the difference between the reversible and irreversible processes. Okay. All right. So in addition to reversible, process can be classified into reversible and irreversible, but processes can be also classified into a few special cases, okay? So constant volume process, for example, when you are changing. So basically for constant volume process, you are not changing the volume of the system, okay? So if you still look at the PV diagram, PV plot. And then we are basically saying that for state 1 to state 2, the volume is not changing, okay? And then for this particular, let's say this is your state 1, this is your state 2, we try to analyze the first law, okay? du is equal to dq plus dw, still the same. dw is minus pdv, same. All right, now the constant volume concept kicks in, right? So for constant volume, dV is equal to 0. Then you can quickly realize du, internal energy of your system change, is equal to dq, right? If you take the integral, then delta U, the change in internal energy of your system, is just equal to the heat exchange between the system and the surrounding, okay, for constant volume process. So delta U equal to Q for constant volume process. Now we can also define the heat capacity, constant volume heat capacity specifically. Usually we use CV. Now, CV by definition is going to be dq dt constant volume, right? So basically, when you receive a certain amount of heat, how your temperature is going to rise, okay? And then this is essentially equal to partial U, partial T, constant volume, right? So because the Q is just equal to delta U, or dQ is equal to du. So here we can just use partial U, partial T, B, okay? Now, and then if you take the integral of this equation, then delta U is just equal to Q, and then it's just equal to T1, T2, CV, dt, right? So basically you change from T1 to T2. If CV is constant, right, then you can take CV out. And then how much heat you exchange between the system and surrounding will cause to a temperature rise or decrease, right? And then that's the temperature rise or decrease can be actually directly calculated by using Q divided by CV, okay? All right, now CV are material dependent, right? So we actually have a table compiling all the CV values for all different type of materials. And usually for ideal gas, CV is a constant value, okay? And then second special process we are interested in is this constant pressure process, right? The constant pressure process, as we are talking about here, let's say this is your state 1, and then you basically go from here to here. You're just expanding, but the system pressure is holding constant, okay? And then in this particular process, what we can start from enthalpy. Enthalpy is by definition equal to internal energy plus PV, okay? And then differential form dH is just equal to du plus dPV, right? You put d in front. And then du, we already know, is equal to dq minus pdv, right? And then dPV is equal to pdv plus vdP, right? So this is just from the first law. This is just like expanding this dPV. And then if you do, rearrange, right, this cancel. So in the end, dH is equal to dq plus vdP. Now, since this is a constant pressure process, then dP goes to 0. If dP goes to 0, then dH is just equal to dQ, right? Similar, like my previous slide, is du is equal to dQ, right? If you take the integral of this equation, then delta U is equal to Q, okay? And then again, this only applies when you are talking about a constant pressure process. So similarly, we can define a constant pressure heat capacity. Constant pressure heat capacity is Cp dq dt, holding pressure constant. And then this is just equal to partial H, partial T, constant pressure, right? Analogous to CV definition in the front, in the previous slide. Okay. And then if you take the integral of this equation, right, delta H is just equal to Q, equal to, integral from T1 to T2, Cp dt. Again, if your Cp is constant, you move to the other outside. And then how much heat you absorb or give out will lead to a temperature rise or decrease. And then that temperature decrease difference between T2 and T1 can simply be calculated by using Q divided by Cp if Cp is constant. Okay. All right. So this is like the definition of the constant heat capacity. In the previous slide is the constant volume heat capacity. And then again, similarly, the constant, the Cp value are material dependent. And again, for ideal gas, Cp is constant. And then for ideal gas, Cp is equal to Cv plus R. R is gas constant. Okay. All right. So the third process that we are interested in is going to be isothermal process. And let's say if we are focusing on ideal gas, more specifically. And previously, I told you ideal gas on the internal energy only depends on temperature. Okay, it doesn't depend on pressure. What does that mean is that since your temperature is constant, dT is equal to 0. And then if if T is not changing, your internal energy is not changing. So du is equal to 0. Okay. Now, if you apply the first law, delta U is equal to Q plus W. And then we know delta U is equal to 0 if isothermal for ideal gas. So it essentially is equal to 0. So in this case, Q is equal to minus W, right? So now here, this equation actually gives you a design rule to convert heat into work, right? So if you absorb heat, right, Q is greater than 0, and then your work is going to be negative. And then basically your system is expanding and then doing mechanical work and then giving work output by ideal gas expansion. Okay. So basically, if we want to leverage this equation, right, how we can design this process is that basically we have a hot reservoir, okay, at a higher temperature. Like you can imagine, this is like a infinitely large heating source, okay? And then you have a piston, containing a chamber of gas. And then basically what you do, if you want to do work on these surrounding by expanding, gas expansion, what you do is that you bring this piston in contact with the hot reservoir, and then the hot reservoir will supply heat to the gas inside. And then the gas will feel the heat, they will expand, right? And then when they are expanding, they are converting heat into work. Okay. Now, if you, on the other hand, if you like bring, you do the work, right? You expand the piston, but usually when you want to do this work, heat work conversion in a cyclical process, you need to bring the piston back to the original position. So how you can do that is that you detach the chamber from the hot reservoir, and then instead you bring it in contact with the cold reservoir, right? Cold reservoir is infinite large cooling source, right? Then your gas will feel the coldness and then they will shrink, and then the piston will slowly go back to the original, right? And during this process, your Q is actually, your system is giving out Q to the cold reservoir. So your heat is out, like, so Q is negative. In this case, your work is actually positive. In this case, your surrounding is actually doing work on your piston, okay? And then basically this is like by compressing the ideal gas. So usually in the Carnot engine, right, this QC is considered to be waste heat, right? And then QH is really the heating source that you absorb. Okay. All right. Now, if the total W is like the basically the W you do here and then the W you do here, but combine them, if your total W is negative, then you have a net output, right? And then in that case, right, if you come back here to the overall first law, right, if W is negative, then your Q is positive. So total Q is going to be QH plus QC is positive. That means your QH has to be greater than QC, right? QC is negative. Okay. We will come back to this a little bit better when we talk about the Carnot cycle. All right. So now, hope you understand, right? For isothermal process, really, it's like the essence. This is like giving you a ground design principle for converting heat to work. So how can we leverage this and then design an engine that can continuously convert heat to work? Okay. So this is like how we can design. It's called a Carnot heating engine. And this cycle, we already hinted you previously, Carnot cycle actually involve reversible processes. More specifically, it actually converts heat to work via four reversible processes. Okay. And then when we are talking about reversible processes, we actually know the system pressure is always equal to external pressure. We have the maximum network output during expansion, right? And then the Carnot cycle will have the highest efficiency. Okay. So what are the four steps? Four steps is already, we hinted a little bit. So first step is going to be, again, you have like ideal gas inside a piston. And then you bring, the first step is that you bring this whole thing in contact with hot reservoir. And then hot reservoir supply QH to the system and then expand. And then this expansion process is actually isothermal because the hot reservoir, let's say your hot reservoir temperature is at TH, right? So your system will maintain at TH and then they will expand until the system pressure is equal to the external pressure. Okay, so 1 to 2, step 1 is isothermal expansion at TH. And then you after expansion, right, you will just like detach the whole thing, and then it will still continue to expand a little bit. Okay, so but in this case, we actually make this process intentionally to be an adiabatic expansion. Adiabatic means you no longer have any heat exchange between the surrounding and the system. Okay. So the system is going to be, at the beginning will be TH, right? Now, when the system is expanding, right? Remember PV is equal to T, right? If V is expanding, then what it happens is that you are doing work on the system on the external surrounding, then you have to decrease in internal energy. So your T temperature is going to drop since you don't have like heat supply, right? So Q is equal to 0 during this adiabatic expansion. TH drops to TC slowly, okay? And TC is the cold reservoir temperature, okay? And then what you do is that you bring this whole system, after this adiabatic expansion, you bring this system in contact with the cold reservoir. And then the system will slowly contract, right? And then we'll do isothermal compression at TC, okay? And then you go back, so you apply some work, and then you are doing some compression back to the original state. Okay, no, back to you are compressing at TC. Okay, and then finally you do some adiabatic compression. So Q is equal to 0, and then TC goes back to TH. So the reason why we want to do this, like, close the loop, basically we want to make this process cyclic, so that you can continuously convert heat into work, okay? So you start from here. After this whole full processes, you go back to the original state, okay? Now, if we plot this on the PV diagram, it will be more straightforward, right? So here is y-axis is pressures, x-axis is volume. And then step 1 is 1 to 2. Like I said, this is going to be isothermal expansion at TH, right? This is like, again, if we follow ideal gas law, then you will have like a curve like this, right? You can go back to see at the beginning when we talk about that. It will show a similar plot like this, okay? And then during this isothermal expansion process, remember we are receiving heat from the hot reservoir, right? And then after that, you are doing adiabatic expansion, and adiabatic expansion from 2 to 3. Like I said, right, your system is still expanding. And then your temperature is dropping from TH to TC because your internal energy is dropping. You are still doing mechanical work to the surrounding, right? And then as a result, your pressure will also drop, right? Because PV equal to RT, right? P is equal to RT divided by V, okay? So your temperature is dropping, your volume is increasing, so your pressure will drop, okay? And then 3 to 4 is isothermal compression, right? So T is TC, so you will have a similar curve like this, but you go from 3 to 4. And then remember here you are removing some heat, right, from the system. So you are actually QC is equal to is negative, right? And then finally you do adiabatic, right? Adiabatic Q is equal to 0. Same thing when you are doing adiabatic compression, your system pressure is increasing, your volume is still decreasing, and your temperature is increasing, okay? So this is like the Carnot cycle on a PV diagram. And then just like write them down, 1 to 2 isothermal expansion at TH, 2 to 3 adiabatic expansion, Q is equal to 0, 3 to 4 isothermal expansion at TC, and then 4 to 1 adiabatic compression, Q is equal to 0, right? Now for the whole cycle, right, then delta U is equal to Q plus W. This is always true, right? Now we are just analyzing the whole cycle. Now the whole cycle, how much work we have done, right? Because isothermal ideal gas is equal to 0, right? Going from 1, complete the cycle, coming back to 1, okay? And then W is going to be equal to minus Q, right? The total Q is just equal to QH plus QC, okay? So if you would imagine, right, for a complete Carnot cycle, what you are doing is that you are receiving heat from the hot reservoir. You are converting this heat into mechanical work. But the issue is that we cannot convert all the heat to mechanical work. You will have to have some waste heat because you want to bring the system back to its original state. So you will have some waste heat, and then the efficiency is basically the network produced divided by the heat you absorb, right? This is your heating source, how much heat you receive, and then how much work you actually converted, okay? So this is called thermal efficiency, eta, right? Eta is equal to, mathematically, eta is equal to the absolute value of this W divided by absolute value of QH, right? Like I mentioned, W is equal to this, but because we having absolute value here, QH plus QC, and QH absolute value in QH is equal to is greater than absolute value of QC. So this is going to be a positive value, okay? Divided by QH. And then it's going to be 1 plus QC divided by QH. So this is the Carnot cycle efficiency. 1 plus QC divided by QH, okay? Now we can actually analyze this process step one by one, and then actually calculate the Carnot cycle efficiency based on the temperature TH and TC here. This is elaborated on this slide. But I'm not going to go over why, right? For process QH, isothermal QH is going to be minus W1. But here, right, the work we done, we already show you how to calculate the work done during this isothermal expansion, which is equal to this, right? So we are not going into detail. And then for 223 is adiabatic. So WQ is equal to 0. Then W is really just equal to delta U. And delta U, like I mentioned, for ideal gas, it only depends on temperature, right? And then since this is, so you can use like CV delta T, right? So here, and then for 324, right, it's mimicking 122, and 421 is mimicking 223. Okay. If you are interested, we have like slides on additional slides at the end of this lecture. You can go to those slides to see how all these equations are derived. Okay. But now you can actually, once you understand the each step, you can actually combine them and then calculate the total work, right? Total work is equal to sum all up, right? But this one and this one actually cancel each other. So in the end, you actually need to worry about W1 and W3, okay? And then for the cycle, we know it's going to be equal to minus QH minus QC, okay? Because it's a negative value. And then you can plug all these back in, right? And then you can convert, basically, you can bring in these TH, TC values instead of QH and QC, okay? And then at the end, you go back to this definition equation, you plug everything back in. Eventually, what you will get is that eta is equal to 1. This is the equation on the previous slide, but now you can actually see it's just like very simple, is equal to 1 minus TC divided by TH. So if you know the hot reservoir temperature, if you know the cold reservoir temperature, if you want to operate a Carnot cycle between these two temperatures, you can actually theoretically calculate the Carnot cycle efficiency, which is just equal to 1 minus TC divided by TH, right? So that's your Carnot cycle efficiency. Now, if you have a perfect engine, meaning that you can actually convert all the heat to work, right? Then your efficient, right? Then your QC is equal to 0, W is equal to minus QH, so your efficiency is equal to 1. But we don't have a perfect engine, right? Carnot cycle actually give you the highest efficiency already if you operate between hot reservoir and cold reservoir, and usually TH is going to be greater than TC. So you know this is going to be a finite value. And then Carnot cycle efficiency is going to be smaller than 1. And Carnot cycle efficiency is already the highest possible efficiency because it involves reversible processes. Okay, that actually gives the foundation of the second law of thermodynamics that we will talk about in a minute. Now that's like Carnot cycle heat engine, right? Heat engine is basically converting heat to work. And then Carnot cycle can actually run in a completely reverse manner. So basically you go from here, compress, and adiabatic compression, isothermal adiabatic expansion, and then isothermal expansion. And then here, right, really you are doing compression at a higher temperature. So basically reverse the cycle. And then what you are doing is that you are drawing heat away from a cold reservoir and then dumping to a hot reservoir. Just imagine your refrigerator, right? So basically you are trying to grab heat from already a lower temperature refrigerator and then dump the heat back into the environment, which might be like, 35, 25 degrees C, but the refrigerator is like maybe 0 degrees C. Okay. And then basically, in order to do that, right, you actually need to do some mechanical work. That's why we usually use a compressor in the refrigerator. So you actually do the compression, you apply the compression work to draw the heat from the cold source to the hot source, hot reservoir. This actually also lay the foundation for the second law, like heat always transfer from hot to cold, like spontaneously. We will talk about that later, okay? But in order for you to draw heat from cold reservoir to hot reservoir, you actually need to do some external mechanical work, okay? All right, so like I said, if you run this reversibly, in the reverse, you are actually doing a Carnot refrigerator. And similarly, I'm not going into detail, but you can also similarly define a Carnot refrigerator efficiency, which is going to be QC, right? How much heat you pulled away, divided by how much work you actually need to perform, right? And then you can do the math, and then eventually your Carnot refrigerator efficiency is just equal to TC minus TH, divided by TH minus TC, okay? So this is how you calculate Carnot refrigerator efficiency, right? If you have a perfect refrigerator, you don't need to do any work. W is 0, so Q, this is 0, then you will get an infinite efficiency, but that's not possible, right? All right, so now from Carnot cycle, right, from Carnot theorem, we can actually, we already hinted you, Carnot theorem is really just like building the foundation for second law of thermodynamics. So basically through this Carnot cycle, we actually discover entropy, okay? So here, from Carnot cycle efficiency, Carnot engine efficiency, 1 eta is equal to 1 plus QC divided by QH, or equal to 1 minus TC divided by TH, right? And then Carnot engine, remember heat engine operating via completely reversible processes, right? Highest efficiency already converting heat to work, okay? What we said, right? If you are talking about a cold reservoir versus a hot reservoir, then TC is going to be smaller than TH. So this value is going to be between 0 and 1. And then you can quickly realize your efficiency is always going to be smaller than 1 for a Carnot engine, right? But we already said, right, for Carnot engine, it comprises completely reversible processes, which are very slow, but in reality, right, we cannot like really operate our heat engine through these like completely reversible processes. So in the end, right, for a given TH and TC, no engine can have a higher efficiency than Carnot engine, right? So with that being said, then basically this tells us like the second law of thermodynamics. So second law of thermodynamics, we have two statements. One is a Kelvin-Planck statement, meaning that no apparatus can operate in such a way that its only effect is to convert heat absorbed by a system completely into work. In other words, our heat engine efficiency is always going to be less than 1, right? Because the Carnot cycle is already less than 1, and all other heat engines are smaller than this. So obviously, you cannot have a perfect engine that only converts heat to 100% into work, okay? So this is the Kelvin-Planck statement of second law of thermodynamics. We also have like a Clausius statement. Basically, this is like no process is possible, which consists solely the transfer of heat from a cold reservoir to a hot body, okay? So basically, in other words, heats always spontaneously flow from hot to cold, okay? And then this process is actually an entropy increasing process. So that in the end, entropy tends to increase, okay? We will introduce you entropy on the next slide. All right. So that's like the statements of second law of thermodynamics. Now let's try to understand a little bit better, right? So for Carnot cycle of a reversible process, we already get this equation, right? And then if you rearrange this equation, then QC divided by QH is equal to minus TC minus TH, okay? And then you rearrange, you will quickly realize QH divided by TH plus QC divided by TC is equal to 0. Now, if you go back to the Carnot cycle and then we do a closed integral of the Carnot cycle, and then well, for the system, you can pick a specific working fluid, and then the same thing, you can pick 1 kilogram of working fluid as your system. And then you try to analyze the closed integral of this particular value, right? Let's say quantity dH, dq, divided by t. I'm trying to ask you to do a closed integral of dq divided by t, okay? So now if you go back to Carnot cycle, right? If you do this integral, first cycle is right here, you supply heat, then dq, if you take the integral, right, from 1 to, yeah, let's go back. Yeah, from 1 to 2 is basically the Q that you receive, right? So the integral dq is just equal to QH. And then since this is an isothermal process, so that T on the bottom is constant, right? Adiabatic, Q is 0, dq is 0, so you are not changing, right? You don't need to worry about this. And then here, like dq integral, since it's again isothermal at Tc, right? dq integral dq is going to be just like Qc, right? And then again, don't worry about this. So if you do a Carnot cycle integral, Carnot cycle again, reversible process, okay? If you do that integral, you will quickly realize, right, this closed integral is equal to QH divided by TH plus QC divided by TC is actually equal to 0 from this efficiency equation, okay? Now that means the closed integral of dq divided by t is actually equal to 0, okay? And again, this only applies for a reversible process, okay? So for Carnot cycle, the closed integral of dq divided by t is equal to 0. And then remember, we talked about that in lecture 1, right? If we have closed integral equal to 0, that means highly likely this is related to a state function or thermodynamic property, okay? All right, so this is for Carnot cycle, right? But what if we have an arbitrary cyclic reversible process, okay? So we don't specify how it goes, like, you know, you can achieve like a really complicated cyclic process, but we say we do it very slowly, and the system pressure is always equal to external pressure, so it's a reversible. So you do this, and then we want to understand when you do this closed integral, right, what is the value going to be, right? So we give you this process. And then what we can do is that we can split, you know, differentiate this whole process into many, many small Carnot cycle, right? You do, you take a section like here, and then you do isothermal, and then adiabatic, you go back, right? You just basically split into this whole cyclic process into many, many small Carnot cycle. And on each Carnot cycle, right, you will have like this fulfilled, right? If it's a Carnot cycle, you know this is going to be 0, okay? And then if you combine all the Carnot cycle, right, you can kind of see right here, if we follow a Carnot cycle like this, right, the adiabatic compression part will be the adiabatic expansion from the other cycle. So if you sum them up, they will cancel, right? These will cancel, right? So in the end, everything, if you combine all the Carnot cycle, you will quickly realize this closed integral is still 0. So this equation not only applies for Carnot cycle, but also for any reversible cyclic process. Okay, so closed path, the closed integral of dq divided by t is equal to 0. Okay, now this is how we define entropy, right? So define the definition of entropy is basically this equation: ds, s is entropy, ds is equal to dq divided by t. But note that this q has to be the heat exchange or transfer under a reversible condition. Okay, and then basically entropy, changing entropy is defined as the heat transfer under a reversible condition divided by T. T is the temperature, system temperature. Okay, so ds is equal to T dq reversible divided by T. You can also rearrange dq reversible is equal to T times ds. Okay. And then I want to just like quickly highlight, right? The closed integral of dq divided by t is 0. But remember, right? Your closed integral of your dq itself is not equal to 0. It's just equal to qh plus qc. And then we know qh is going, absolute value of qh is greater than absolute value of qc. So this is non-zero. That's why, that's how you can get work output, right? So this integral is 0, but not dq reversible. Okay. And then since we already know the closed integral of this guy is equal to 0, so the closed integral of ds is equal to 0. So basically, closed integral of ds is equal to s initial minus initial is equal to 0. That hints us that entropy is indeed a thermodynamic property or a state function, just like your internal energy or your enthalpy. Okay. And then if you now want to calculate the entropy change from state 1 to state 2, basically you just need to delta S equal to S2 minus S1. You take the integral dq divided by t. Okay. And just like to quickly summarize, ds is dq divided by t. Entropy is a thermodynamic property. Change of S between two states is not path dependent, right? That's like a characteristic of a thermodynamic property. And then delta S between any two states can be calculated by an arbitrarily chosen reversible process. Since, right, it's not path dependent, so you can actually assign a reversible process. And no matter how the actual process is reversible or not. So going from state 1 to state 2, the entropy change doesn't depend on the actual process you occur. But you can actually just pick a reversible process. And then going from 1 to 2, you calculate that entropy change will be the entropy change for the actual process. Okay. And then in the example, in the additional slides, we actually give you some calculations, right? For adiabatic expansion, adiabatic, remember, Q is equal to 0 for adiabatic expansion. Now, if we have a reversible process, right, your delta S for that adiabatic expansion is going to be equal to 0. But if your process is non-reversible, then your delta S is actually going to be greater than 0. Okay. So if you want to know more about that, you can read the additional slides in terms like how you derive that. Okay. But just remember, for adiabatic expansion process, if it's reversible, delta S is just equal to 0. Okay. Now, finally, I want to comment on the Clausius statement on the second law of thermodynamics, meaning that heat always spontaneously flow from hot to cold. And then the underlying statement is that usually the universe prefer a entropy increasing process, or entropy tends to increase. Okay. All right. So in order to derive that or to prove that, right, we can imagine an isolated system. And then within this system, we actually have a chamber. You have a separator between, hot body and the cold body. Okay, so you have like an interface. Okay. And then we just like initially they are not in contact. Okay, so they are TH and TC, but we bring them together. Okay, let TC and TH like let these two bodies touch. And then imagine, right, the heat, hypothetically, the heat will flow from TH, hot body to cold body, and then we eventually reach equilibrium state, which is like, they reach the same temperature TF, okay? And then we want to calculate for this particular process, right, what is the entropy change? What is the change in entropy delta S, okay? So now what we can do, right? We can calculate the change of entropy change for your hot body, right? Hot body delta SH is going to be QH divided by TH, right? And then this QH, the amount of the heat transfer is, you're giving out Q away, and then cold body is receiving Q. So you can just say minus absolute value of Q divided by TH. And then for the cold body, right, delta S is equal to QC divided by TC, okay? And then the total entropy change is equal to delta SH plus the delta SC. And then you can combine things. And then here, since TH is greater than TC, you will see, right, delta S total is always going to be a greater or equal than 0, right? So delta S is increasing or remain constant, okay? So that means recall the second law, right? Statement 2, no process is possible when which consists solely the transfer of heat from a lower temperature to a higher one. So that means you cannot spontaneously transfer heat from cold to hot. You have to do external work. But spontaneously, heat will always flow from a hot body to a cold body because that's an entropy increasing process. So the universe prefers the entropy to increase, okay? All right, hopefully in today's lecture, we understand the process, understand the concept of entropy, and then we talked about reversible, irreversible processes and second law of thermodynamics, right? You understand the Carnot cycle, heat engine, and then we really spend time on the second law of thermodynamics, entropy and entropy change for reversible processes. That's all for today's lecture.